Somewhere in the Pacific Theater, 1943, a Marine takes a sip from his new amber-colored plastic canteen. The water tastes like bitter chemicals. He grimaces, tries again. Same result. Within minutes, nausea hits. He's not alone. Across the island, dozens of Marines are dumping their water, reportedly mixing it with baking powder just to make it drinkable, or simply refusing to drink at all in 100-degree heat. The canteen was supposed to save aluminum for aircraft production. Instead, it was making American troops sick. This is the story of how the United States looked at Germany's successful composite canteen and decided they could do better by eliminating metal entirely. They couldn't, and American soldiers paid the price. North Africa, 1941. German soldiers in the Africa Corps carry something unusual. Instead of the standard felt-covered aluminum canteen, many troops have what looks like a coconut strapped to their belts. It's brown, hard-shelled, and covered in what appears to be compressed wood fibers. The Germans call it the Tropenfeldflasche. Everyone else calls it the coconut canteen. Heinrich Ritter's company in Esslingen am Neckar developed this canteen using a brilliant material called Durofol. But here's what made the design work. The water never touched the Durofol. The core of the canteen was a standard aluminum flask, completely conventional, chemically inert, safe. The innovation wasn't replacing the metal. The innovation was replacing the felt covering with something better. The Durofol shell, compressed wood veneer bonded with phenolic resin, wrapped around the aluminum bottle like armor. 3 layers of laminated composite with aluminum fittings at the neck for the cap and closure. The phenolic resin was stable and heat-resistant, but it didn't need to be food-safe. It never contacted the drinking water. The advantage was immediate. The old felt covers absorbed water, added weight, and wore out quickly in desert conditions. The Durofol shell was waterproof, durable, and provided better insulation through evaporative cooling. Most importantly, it saved aluminum, not by eliminating the metal flask entirely, but by replacing the bulky, resource-intensive felt covering with a thin composite shell. The Germans still used aluminum for the actual water reservoir because that was the safe, proven solution. The phenolic resin composite was only the protective outer layer. This was the key to the design's success, a practical compromise that saved some metal without compromising function. From 1941 through 1943, Ritter's factories produced these canteens in massive numbers. They appeared not just in North Africa, but on every front where German forces fought. The coconut canteen worked. It was durable. It kept water cool. It conserved felt and some aluminum. And most importantly, it was completely safe to drink from. The phenolic resin in the outer shell was chemically stable and cured to a hard, inert finish. But none of that mattered for water safety because the water was contained in the aluminum flask, exactly as it had always been. The Germans hadn't tried to reinvent the water container. They'd simply given it a better outer shell. Washington, D.C., early 1942. The War Production Board faces a crisis. Aluminum production can't keep pace with demand. Every B-17 needs 2 tons of aluminum. Every P-51 needs another ton. Canteens? Canteens use aluminum that could build aircraft. The Army Quartermaster Corps desperately searches for alternatives. They try porcelain-enameled steel canteens. The enamel chips. Fragments contaminate the water. Troops complain. The Marine Corps specifically warns that the enamel coating is so fragile that even a small knock causes it to powder and fall into drinking water. Over 5 million enameled canteens are manufactured in 1942 by companies like Vollrath, Singer, and United States Stoneware. Within months, the Army orders them removed from issue at ports of embarkation. They're too dangerous to send overseas. Then intelligence reports arrived describing the German coconut canteen, pressed wood construction, phenolic resin bonding, metal conservation, combat-proven reliability across multiple theaters. The Quartermaster Corps sees an opportunity. Germany proved that non-metal materials could work for canteens, but the German design still used an aluminum core. America, with its advanced chemical industry and thermoplastics technology, could do better. Why settle for a composite shell around a metal flask when you could make the entire vessel out of plastic? The decision is made. America wouldn't just match the German innovation, they would surpass it by eliminating the aluminum reservoir entirely. 100% plastic, zero metal, maximum aluminum savings for aircraft production. It was an ambitious goal, perhaps too ambitious. Midland, Michigan. Dow Chemical Company offers a solution. Since 1935, they've been producing a plastic called Ethocel. It's ethyl cellulose polymer, organosoluble, thermoplastic, easy to mold. Dow markets it for industrial applications, radio housings, toy parts, building materials. Why not the water reservoir itself? The Quartermaster Corps. Technical Committee embraces the concept. Plastic canteens would be lightweight, easy to manufacture. And unlike the German design that only saved felt and some aluminum, this approach would free up 100% of the canteen's aluminum for the aircraft industry where it's desperately needed. In September 1942, Dow molds 10,000 experimental Ethocel canteens. They're sent to various test boards for field trials. The canteens are amber yellow in color. They're made from 2 injection-molded halves, joined at a horizontal seam. They fit the standard M1910 canteen cup. They use the same black Bakelite screw caps as metal canteens. The critical difference, the water sits directly inside the Ethocel plastic. No metal liner, no inert barrier, just thermoplastic and drinking water in direct, prolonged contact. The test results come back, mostly favorable. The plastic canteen is deemed a suitable replacement for the aluminum M1910 canteen. There's just one problem mentioned in the reports. A small issue, barely worth noting. The Ethocel plastic has an undesirable property of transmitting odor and taste to contents. The technical committee concludes that while the taste and odor remain present in all formulations, field tests determined the taste, and odor wasn't strong enough that soldiers refused to drink the water. That assessment would prove catastrophically wrong in actual combat conditions. Pacific Theater, 1943. The first Ethocel canteens reach American forces. Manufacturers include American Insulator Company, Amos Molded Plastics, General Industries, Mack Molding Company, and others. Production authorized for 3.75 million units between 1942 and 1944, though only a fraction of that number were actually manufactured. The initial plan calls for 85,000 canteens in December 1942, 100,000 each in January and February 1943, then 50,000 per month thereafter. Marines in the Pacific get them first. They fill the canteens with water. Take a drink. The water tastes bitter, like plastic chemicals. Some troops describe it as medicinal, others say it tastes like poison. In the tropical heat, the problem intensifies. The sun beats down on the amber plastic. Heat accelerates the leaching process. Residual solvents and plasticizers trapped in the Ethocel during manufacturing begin dissolving into the water at accelerated rates. This is what the Germans avoided by keeping an aluminum liner. The water in a coconut canteen never touched the phenolic resin. In the American Ethocel canteen, there's nothing between the water and the unstable plastic. Troops start feeling nauseated. Many refuse to drink even in extreme heat. This is dangerous. Dehydration in the Pacific Islands could incapacitate a Marine faster than enemy fire. Troops reportedly find a workaround. Mix baking powder with the water when filling the canteen. The baking powder supposedly helps neutralize the bitter taste. It doesn't eliminate it, but it makes the water barely tolerable. Photographs from Pacific Island campaigns show discarded Ethocel canteens littering the routes of Marine advances. Troops threw them away. They were worthless. The water was undrinkable. A veteran later recalls his father, who served in Patton's 6th Armored Division in Europe, was issued one of these plastic canteens. The experience wasn't unique to the Pacific. Wherever the Ethocel canteens went, troops rejected them. The issue wasn't just taste. It was fundamental chemical incompatibility between thermoplastic and prolonged water contact. Ethyl cellulose is a cellulose derivative where ethoxy groups replace hydroxyl groups on the cellulose polymer chain. When properly formulated with plasticizers and stabilizers, it can be relatively inert for short-term industrial uses. But the wartime Ethocel formulation wasn't stable enough for prolonged contact with drinking water, especially under heat stress. The American Ethocel was pure polymer, no filler, no protective barrier. The plastic contained residual solvents and plasticizers from the manufacturing process that hadn't fully evaporated or cured. When water filled the canteen, these chemicals began migrating into the liquid. Heat accelerated the process exponentially. The plastic was also sensitive to temperature. When exposed to heat, it softened. When water was introduced to sterilize the canteen by boiling, the plastic deformed. The canteens developed other problems. Heat stress cracks appeared. If the contents froze, the plastic shattered. The material was unsuitable for heating water over a flame, eliminating one of the canteen's key tactical uses. Alcohol in concentrations of 50% or higher attacked the plastic and destroyed the canteen entirely. The chemical leaching wasn't just unpleasant. The bitter taste came from residual solvents, plasticizers, and unreacted monomers trapped in the polymer during manufacturing. While not acutely toxic in the concentrations present, these compounds were enough to trigger nausea in many troops and cause widespread refusal to drink. This was the fatal flaw in the American approach. By trying to eliminate metal entirely, they put drinking water in direct contact with a material that wasn't chemically stable enough for the application. The Germans kept their aluminum liner specifically because it was inert, proven, and safe. The Americans tried to skip that proven solution and paid the price. Why did the German coconut canteen work when the American Ethocel canteen failed? Practical compromise over technological ambition. The Germans didn't try to eliminate metal from the water reservoir. They recognized that aluminum was the proven, safe material for containing drinking water. Their innovation was replacing the felt covering, the part that didn't need to be metal, with a superior composite material. The Durofol shell, compressed wood veneer bonded with phenolic resin, provided protection and insulation. The phenolic resin in the shell was chemically stable and thermally cured, with polymer chains cross-linked into a rigid, non-reactive structure. But none of that mattered for water safety because the water never touched the resin. The wood fibers in the Durofol acted as reinforcement and reduced the overall resin content to only 25%. The bulk of the composite was wood, not plastic. This created a material that was strong, stable, and cheap to manufacture. But the key insight was architectural. The Germans understood that some technologies should be proven and reliable, not experimental. The aluminum water reservoir was proven technology going back decades. The phenolic composite shell was the innovation. Keep the core proven, Innovate on the periphery. The American approach reversed this wisdom. They kept the proven technology, the Bakelite screw cap, and made the core function experimental by using thermoplastic for the water reservoir itself. They innovated where reliability mattered most and kept tradition where it mattered least. November 1942, the Quartermaster Corps Technical Committee recommends the plastic canteen for production, classified as substitute standard for the Canteen M1910. Authorization granted for 3.75 million units. But something changes. In November 1942, the War Production Board releases aluminum and stainless steel for canteen production again. Suddenly, the desperate need for plastic canteens evaporates. The initial ambitious production schedule gets quietly reduced. By 1943, as aluminum becomes available, plastic canteen production drops dramatically. By 1944, it effectively stops. Many surviving Ethocel canteens bear a stamped marking, IC inspected and condemned. The official meaning is that the equipment is no longer needed or has been rendered obsolete. The unofficial meaning understood by every soldier who tried to drink from one is simpler. They didn't work. They made the water taste like chemicals. They were abandoned in the field. Today, Ethocel canteens are rare collector's items. Most are found with stress cracks. Many reportedly have a white powdery residue inside from the baking powder troops allegedly used trying to make the water drinkable. They're artifacts of technological overreach. The German coconut canteen, by contrast, remained in production through 1945. The design was so successful that after the war, similar composite construction techniques influenced commercial and military equipment worldwide. The canteens were durable, safe, and effective. They achieved exactly what they were designed to do, save some materials without compromising function. The failure of the American Ethocel canteen reveals a fundamental truth about technological competition. Trying to leapfrog proven success with untested ambition often leads to disaster. The Germans developed the coconut canteen through practical engineering. They identified what could be changed, the outer covering, and what should remain proven, the metal water reservoir. They chose phenolic resin and wood composite for the shell because it was durable and saved materials. But they never questioned whether aluminum should remain the material for the actual flask. That was proven technology. That was safe. The Americans saw Germany's success with composite materials and decided to go further. Why stop at replacing the covering when you could replace everything? They chose ethyl cellulose because it was available, moldable, and promised to eliminate 100% of the aluminum. They assumed that if phenolic resin could work as an outer shell, then thermoplastic could work as a water reservoir. They were wrong. The two materials served completely different functions and faced completely different chemical challenges. Phenolic resin on the outside of a canteen experiences sun, sand, and mechanical stress. Ethyl cellulose on the inside of a canteen experiences prolonged water contact, heat stress, and chemical stability requirements. The Germans understood this distinction. The Americans didn't. The result was predictable. Troops in the Pacific drank bitter, chemical-tasting water, felt nauseated, and threw the canteens away. The program was quietly scaled back once aluminum became available again. Most of the 3.75 million authorized canteens were never manufactured. Those that were issued were quickly removed from service. The irony is profound. Germany, desperately short on strategic materials, developed a material-saving canteen that worked by recognizing what needed to remain metal. The United States, with vast industrial resources and advanced plastics technology, tried to eliminate metal entirely and created equipment so flawed that troops preferred to risk dehydration rather than drink from it. Sometimes practicality beats ambition. Sometimes a partial solution is better than an overreaching one. Sometimes the boring, proven technology should stay exactly where it is. The Germans succeeded because they made a practical compromise. Save material where you can, the outer covering. Keep proven technology where you must, the water reservoir. The aluminum core wasn't a failure of imagination. It was recognition that some engineering problems were already solved and didn't need reinventing. The Americans failed because they tried to eliminate what shouldn't have been eliminated. The aluminum water reservoir was proven, safe, and reliable. Replacing it with experimental thermoplastic wasn't innovation, it was overreach. And in 1942, the technology simply wasn't ready. The chemical stability required for food-safe plastics in prolonged water contact wouldn't be fully achieved until decades later, with materials like high-density polyethylene and polypropylene. In trying to leapfrog to that future in 1942, the U.S. Army created canteens that made water taste like chemicals and caused troops to feel sick. The Germans understood this limitation. They used phenolic resin where it didn't touch water and aluminum where it did. It wasn't glamorous, it wasn't revolutionary, but it worked. The Americans tried to revolutionize everything at once. They paid the price in abandoned equipment, nauseated troops, and a failed program that's remembered today only as a cautionary tale. One canteen succeeded through practical compromise, metal core, composite shell. The other failed through technological hubris, eliminate the metal entirely. The difference wasn't copying versus innovation, it was wisdom versus ambition. And in World War II, on Pacific Islands where water meant survival, wisdom won. If stories like this, where technological ambition collided with practical limits, interest you, hit that like button and subscribe. Next time, we're covering another piece of World War II technology where overreach changed everything.